Moitra, who will speak on polynomial methods in learning and statistics.
Great, thanks. Great to be here. Thanks for coming. So my goal today is to tell you about some of the emerging applications of polynomial methods in both learning and in statistics. In particular, I'll give you two examples from my own work on the problem of learning mixtures of Gaussians and on the problem of computing the non-negative rank of a matrix, in which well-studied problems in learning and in statistics can best be understood through the language of algebraic geometry. And the first part of the talk that I'll be telling you about is based on joint work with Adam Kalai and Greg Valiant. And I'll also tell you about independent work of Mikhail Belkin and Kaushik Sinha done on this same problem. So let me introduce the problem of learning mixtures of Gaussians through a story that dates back to the famous statistician Karl Pearson back in 1894. Pearson was very interested in evolution. In fact, there was a particular species of crab called the Naples crab that inhabited the region around him. So what he did was he took thousands and thousands of samples from this crab population, and he measured some physical characteristic of each crab. In his case, he measured the ratio of the height of the crab divided by the circumference of its head. And he plotted the frequency of occurrence of different values. But the density function that he got surprised him, because it wasn't Gaussian. In fact, it wasn't even symmetric around its maximum value. So what he offered, he was quite puzzled by this, but what he offered as an explanation was that maybe the Naples crab wasn't just one species of crab, but was rather two, and that the density function he observed could then be explained as a convex combination of the density functions of two constituent Gaussians. He postulated that the data he observed was generated from a mixture of two Gaussians. So he set about the algorithmic problem of trying to determine the parameters of the underlying mixture that best explained his data. So since the time of Pearson, this is a problem that's found numerous applications ranging across many different fields, and even many different techniques have been brought to bear on this problem. But what I'd like to do is I'd like to tell you more in detail about Pearsons' approach, because in a sense, the work that I'll be talking about will be a return to Pearsons' algebraic ideas for solving this problem. So let me be more formal. So the underlying mixture we have, f of x, is a Gaussian mixture model, or in this case, a mixture of two Gaussians. And we can generate a random sample from f as follows. We take a coin which is biased, which is heads with probability w1, and is tails with the remaining probability 1 minus w1, and we flip it. And if it comes up heads, we take a random sample from the first Gaussian and we output it. If instead it comes up tails, we take a random sample from the second one and we output that. So in this way, we can generate a random sample from a mixture of two Gaussians, and the density function is indeed a convex combination of the density functions of the two constituent Gaussians. So I want to emphasize that these Gaussian components need not have the same mean or variance. So really, this distribution is characterized by 5 unknown variables whose values we would want to find. The first parameter is w1, which I'll call the mixing weight throughout this talk. Then we have the mean and standard deviation of the first Gaussian, and the mean and standard deviation of the second Gaussian. And the question Pearson wanted to answer was, if we want to learn these parameters approximately, if we want to learn them within some, say, additive epsilon, can we do so given enough random samples from f? And in fact, Pearson's approach was an algebraic one. It applies to statistical problems more generally and is often called the method of moments. So his idea roughly was to take many samples from the distribution and to use these set of samples to compute approximations to moments of the underlying distribution, and then to use these values to constrain the parameters of the unknown variables. So in particular, Pearson's approach really rested on the following critical observation, that if I take the expected value of x to the r, when I take x as a random sample from the distribution f of x, this quantity I'll call the rth raw moment of a distribution f of x. Well, this quantity is in fact a polynomial in the underlying parameters that we are trying to solve for. In fact, moreover, it turns out that it's a degree r plus 1 polynomial in these underlying parameters. And this polynomial will play a very special role in describing Pearson's approach and also later in this work. So I'll denote it by m sub r of theta to emphasize the fact that it's a function of the underlying variables that we are trying to solve for. So now I can describe Pearson's approach in detail, which his idea was to take many samples from the underlying distribution and then to use this set of samples to compute approximations to the first 6 moments. So these approximations I'll denote by m tilde sub r, and these approximations are computed in the natural way. Namely, we take a random sample x from this set of samples, and we compute the expected value of x to the r. So these I'll sometimes call the empirical moments of the distribution, which have noise. These are not exactly the true raw moments of the underlying distribution. So now Pearson's approach was to set up a system of polynomial equations. In fact, what he did was, so on the left-hand side we have this polynomial and the parameters we're trying to solve for. And on the right-hand side we have a scalar value, which is the function of our data. And he had 5 unknown variables he wanted to solve for. So his hope was just to set up a system of 5 polynomial equations, and that this system of polynomial equations would narrow the candidate set of parameters down to some much more manageable set. So it's actually quite remarkable. He solved this system of polynomial equations by hand and computed all the different simultaneous roots back in 1894, in fact. And what he did was, some of these candidate roots were clearly not the right answer. Some of them would have negative values for their mixing weights, or some of them would have negative values for their variance. So those were not the solution he was looking for. He threw those out, but he was still left with more than one candidate solution, more than one set of roots, which, if those were the parameters of the mixture, would explain the first 5 moments he observed. So he had to decide how to choose which among them was what he thought would be the real set of parameters. And his approach was a heuristic one, but it was to use the 6th moment as a tiebreaker. Each of these remaining candidate sets of parameters, it yields some analytic prediction of what the 6th moment would be if that really were the set of parameters. So for each of those remaining sets, he computed what the 6th moment would be, and he compared it to the 6th moment he observed in the data. And he chose whichever one was closest to the observed 6th moment. So this is called Pearson's 6th moment test, and as I mentioned, this approach applies more generally, is often called the method of moments in statistics. And I'll return to this method later, but for now, what I want to emphasize is the fact that Pearson's approach is based on taking finitely many samples from the distribution. So in fact, these empirical moments will not exactly match the true moments of the distribution. There's inevitably some sampling noise just because we've taken only finitely many samples. So Pearson very explicitly asked how this inevitable noise in the empirical moments he observed translated to noise in the derived set of parameters. And we'll come back to that question. But let me tell you a little bit more about the history of this problem. Following Pearson, Fisher founded a rival school of statistics, which was based on more information theoretic principles. And in fact, he popularized the maximum likelihood estimator, which to this day is a mainstay within parametric statistics. And its popularity is owing to great properties that hold in the limit. But for now, I'll mention that the real downside to this estimator is that it's computationally hard. It's too computationally expensive to compute the maximum likelihood estimate in many scenarios of interest. So the first person to actually establish that even in principle this problem can be solved was Teicher, who established what's called identifiability within the statistics community. He showed that given perfect knowledge of the underlying distribution, that this in fact defines what the parameters of the underlying mixture are. And his approach was to establish identifiability through the very tails, through the very extremes of the function. Because his critical insight was that the behavior of the density function in the very extremes was dominated by the maximum variance component. So from the behavior in the very extremes, we can determine the parameters of the maximum variance component, subtract it off, and recurse. But this, too, is also not a computationally efficient approach just because it takes too many samples. These samples in the tail are very, very rare. So if we're getting random samples from the distribution, this really isn't a computationally efficient estimator just because, yep?
This was, so Pearson, I mean, how did Pearson, what did Pearson think of identifiability?
He definitely cared about that, but he certainly emphasized more the issue of how this noise in the parameters. So he actually almost took it for granted that if there was no noise in the moments, that it really would recover. It's always good to be grilled by your co-authors. Dempster, Laird, and Rubin proposed a more local search-based approach, which is often called the expectation maximization algorithm. And this has been a very powerful approach in practice, but this too has its downsides, namely that it can get stuck in local minima. And even worse, empirically, it's been observed to take a very long time even to converge to this suboptimal answer. But perhaps the work that's most similar to the work that I'll be talking about in this talk is the work done within the theoretical computer science community, starting with the pioneering work of Dasgupta, in which the approach here is to make assumptions about the underlying mixture so that one provably can learn the underlying parameters. And all of these approaches were fundamentally based on clustering. They're based on the idea take many samples from the distribution and figure out with high probability which component generated each of these different samples. But the problem is that these approaches need to make very strong assumptions about the underlying mixture. They need to assume that the components are quite far apart from each other, namely that these components are almost non-overlapping. So in fact, in summary, really, a lot of these approaches either fit under the category of being heuristics or are based on computationally tractable estimators, or make an assumption about the underlying mixture to guarantee that you can learn the underlying parameters. And there's still quite basic questions, surprisingly, not known about this problem. Namely, Pearson's original question, which I hope he would have formulated this way if he had the language, would be, if you want to learn the parameters to within some additive epsilon, can you find an algorithm whose running time and sample complexity are polynomial? So in fact, what I want is an algorithm with provable guarantees whose number of samples and running time is bounded by some fixed polynomial in 1/epsilon. And in fact, in joint work with Adam Kalai and Greg Valiant, we showed that a positive answer to this. We showed that there is an algorithm. In fact, this algorithm even works in high dimensions. So given a high-dimensional and n-dimensional mixture of two Gaussians, our algorithm requires a number of samples which are polynomial in n and 1/epsilon. And the running time, moreover, is also polynomial in n and 1/epsilon. So this is actually, within polynomial factors, the minimum, the information theoretic minima you could hope for. And in principle, and in fact, it returns an estimate, which itself is a mixture of two Gaussians, which is close to the true mixture on a component-by-component basis. So there's a matching of the components in our estimate to the components in the true mixture, so that across this matching, the parameters are within epsilon. So really, the focus of this talk will not be on the high-dimensional problem of learning mixtures of Gaussians. So I'll just briefly mention what we do in high dimensions, which is that we put the mixture in isotropic position, and we use random projection to reduce it to a series of one-dimensional learning problems. Instead, what I will focus on is what we do in one dimension. Namely, to get a univariate learning algorithm, we in fact analyze Pearson's algorithm, Pearson's sixth moment method, and we show that it does provably work. First of all, we show that if you're given the true values for the first 6 moments, then it does return the true parameters. In fact, those parameters are uniquely defined. But moreover, even if you're given noisy estimates for the first 6 moments, if they're noisy but they're sufficiently close to the first 6 moments, the true moments, then you actually can recover an estimate for the parameters which is also sufficiently close.
What if you have more than 2 Gaussians?
We can do that as well, but I won't focus on this in this talk. So actually for k Gaussians, well, the number of moments that we need is 2k minus 2. There are a lot of more technical things that go on, especially in the high-dimensional algorithm for k Gaussians, but exactly the same algorithm will work in the univariate case. So I'll describe that later. Yep.
Yeah, and what about do you have some conjecture or estimate on what this polynomial is? What the degree?
Yeah, we know exactly. This?
N to the 147 and 1/epsilon.
What do you expect?
I expect that it'll be a slightly more interesting answer than the statisticians expect.
What do the statisticians expect?
2 or 4. If you give them 3, they won't believe it. If you give them 5, they won't believe it. I think it's more interesting than that.
Yeah. So I So,
Yeah,
you know,
but
so
that
the thing we
would-
prove is there's no effort to,
No, I understand.
yeah. But the true answer is actually a slightly worse polynomial than you might expect. So, yeah, it might be,
As long as it's 6 or something.
yeah. It's easy to construct examples where it's at least 4.
Okay, so in fact, now what I want to focus on, keep in mind the following goal. We want to show that, eventually we want to show that noisy estimates for the first 6 moments work, in this case of learning mixtures of 2 Gaussians. But let me start with a much easier question in principle. Suppose we're not given noisy estimates for the first 6 moments. What if we're given exactly the first 6 moments? We're given exact values for the first 6 moments. Well, in fact, do these values exactly characterize the parameters of the underlying mixture? So this will be the first question that we'll attack, is showing that actually the first 6 moments do suffice to determine this. And I'll add the caveat that you can't distinguish which component is component 1 and which one's component 2. That's arbitrary. So really, you want it to uniquely determine the parameters of the mixture up to a relabeling of the 2 components. And in fact, an equivalent way to phrase this question, which is maybe a little bit easier to think about, is what if I have 2 different mixtures, f and f hat, of 2 mixtures of 2 Gaussians? So these are different in the sense that their density functions are not exactly equal. Well, what if I have 2 different mixtures of 2 Gaussians, f and f hat? Do they necessarily differ on at least one of their first 6 moments? And this is what we're going to work towards proving right now. Any questions? Okay, in fact, let's do the following thought experiment. Suppose we had one mixture of 2 Gaussians denoted by these red components, and we have another mixture of 2 Gaussians denoted by these blue components, f and f hat respectively. What if we pointwise subtract their density functions? That's some function on the real line. And I claim that what the core of the issue now is how many times does this function cross 0? This is the core issue. In fact, why is this the core issue? And then we'll come back to actually showing this. Well, it's because once I know that this crosses the 0 axis at most 6 times, then what I can do is I can fit a polynomial to the sign difference. In fact, this polynomial will be, in this case, degree 6.
What's f hat? I missed what you said there.
So f is one mixture of 2 Gaussians. F hat is another mixture of 2 Gaussians. These are their density functions, and you pointwise subtract them. And in fact, now, once we know that f minus f hat doesn't cross the 0 axis too many times, well, what we know is that the integral of this polynomial p of x, which is degree at most 6, well, the integral of p of x against f of x, well, this quantity is not equal to 0. So in fact, its absolute value is strictly greater than 0. And we can now expand this polynomial in the obvious way. We know its degree at most 6, so we're just going to write it out based on what its coefficients are for the first 6 powers of x. And we can then apply triangle inequality to each of these terms. But now consider this quantity right here. We have the integral of x to the r against f of x. And f of x is the difference between the 2 density functions. So in fact, this quantity now, right there, is the difference between their rth raw moments of f and f hat respectively. So in fact, this quantity is strictly greater than 0. So one of the first 6 moments better be different between f and f hat. So now, where are we? The core of what we want to establish is just this question of f minus f hat. How many times does it cross 0? And in fact, to do this, we're going to prove a more general proposition. Suppose I have f of x, which is now a linear combination of k Gaussians. So it's a linear combination because these coefficients alpha sub I are allowed to be positive or negative. And I want to prove that if f of x is not identically 0, then it crosses the 0 axis at most 2k minus 2 times. So in particular, the case that we're really interested in is when you take one mixture of 2 Gaussians, you pointwise subtract another mixture of 2 Gaussians, which itself would be a linear combination of 4 Gaussians. And this would imply that it crosses 0 at most 6 times, and the first 6 moments do indeed determine its parameters. But now we're going to prove this proposition by induction. And in fact, the use of a theorem that's going to sound a little bit strange at first, so I'm just going to state it. And it'll sound sort of magical that it fits exactly into what we need, but then let me try and demystify it after I state it. Which this theorem of Hummel and Guidas tells us that when we take a function f of x on the real line, that when we convolve it by a Gaussian, the resulting function does not cross the 0 axis more times. If it had at most n 0 crossings, then this new function will have at most n 0 crossings counted with multiplicity. So convolving by a Gaussian does not increase the number of 0 crossings.
Do you know Guidas' first name?
No, I don't. Is that Brown?
Okay, no, that's also one I know.
OK. In fact, let me try and demystify this a little bit for you. We can imagine a physical process associated with this theorem. Let's take a function f of x on the real line, which is the heat profile along some one-dimensional rod. And f of x will be the starting heat configuration. Now, what does the heat profile look like at some later time? Well, it should be the original heat profile convolved with a Gaussian of an appropriately chosen variance. So this theorem corresponds to really letting diffusion occur. And so diffusion has very nice, smooth properties, like it would never create a new local maxima, because as soon as you tried to create a new local maxima, there'd be an immediate diffusive pressure to pull it back down. And the same way you can't create a new local minima, because as soon as you try, there'll be a diffusive pressure to pull it back up. And along the same lines, it actually can't increase the number of 0 crossings. So that's all I'm going to say about this theorem, but now let's use this to prove this proposition by induction on K. And I'll use the following well-known fact, that convolving two Gaussians results in a Gaussian. In fact, this Gaussian, the variance, is just the sum of the variance of the two Gaussians on the left-hand side. So now let's prove this proposition by induction on K. So let's assume it for K equals 3. So we know that any linear combination of 3 Gaussians has at most 4 0 crossings. And now let's try and prove it for linear combinations of 4 Gaussians. So we have some arbitrary linear combination of 4 Gaussians. We're going to add up the red components and subtract the blue components. And in fact, what I can now do is I can subtract the same quantity from the variance of all the different components until one of the components becomes a delta function. So I'm subtracting whatever is the smallest variance from all the other components. And now let me ignore the delta function. So here we have a linear combination of 3 Gaussians. So we know, in fact, by induction that the number of 0 crossings is at most 4. But this will be a little bit sketchy in terms of real analysis, but you can make it work. How many 0 crossings do you add when you add a delta function? You can add at most 2, 1 on the way up and 1 on the way back down. So in fact, this linear combination of 4 Gaussians has at most 6 0 crossings. But now what I really care about is the original linear combination of 4 Gaussians, which I can recover by convolving by a Gaussian of the appropriate variance. And that does not increase the number of 0 crossings by the theorem of Hummel and Guidas. So this implies what we're after, that actually the first 6 moments do uniquely determine the parameters of a mixture of 2 Gaussians. And in fact, to answer Shahar's question, it'll also tell you how many moments you need for mixtures of K Gaussians. And now let me actually give you an algebraic restatement of what this is. So what do we know right now? We know that the exact values of the first 6 moments determine the mixture parameters. And what we want to show is that even noisy moments suffice. But let me first give an algebraic restatement of this result. Namely, I'll consider a set of valid parameters, which not every setting of the 5 underlying variables really corresponds to a mixture of 2 Gaussians. Because implicitly, we're assuming that the mixing weights be between 0 and 1, and we're assuming that the standard deviations be non-negative. So this set of valid parameters will just be a linearly constrained set. Yep?
So can't you, for example, break things where assuming that W1 is at least half?
Yeah, you could. Yeah, and then, one second. Yeah, you could do that, and then something I'm going to say would be true just, with instead of 2 possible solutions, it'll only be 1. But In any case, I can define the following variety. So I'm going to consider theta as the true set of parameters that are hidden. And I'm going to consider theta prime as a set of variables. So I need theta prime to be a valid set of parameters. But moreover, what are the constraints that theta prime really match the first 6 moments of theta? They're a system of polynomial equations. This is exactly what Pearson used. So in fact, we have a system of polynomial equations for r from 1 to 6, which we now know what are the solutions to the system of polynomial equations. There's only 2 solutions, the real parameters and the ones where we interchange which one is component 1 and which one is component 2. Because there's no other mixture of 2 Gaussians which doesn't match, which agrees on the first 6 moments. But really, if we want to understand how the method of moments behaves under noise, what we're really asking is, in a sense, how stable are these equations? In a sense, how much does the solution change if we perturb the right-hand sides of these equations? So in fact, what we really need to establish is, in essence, is a type of condition number for this, that if you change the moments, the empirical moments, by only so much from what the true moments are, that you haven't changed the solution by too much. And I won't prove this, but I'll mention that we can use similar ideas of using deconvolution, namely subtracting the same quantity from all the different variances, to try and isolate components and reason about the mixture. In fact, we can show that there are constants C and capital C, so that if the means and variances and mixing weights are all suitably bounded, that in fact, if you have 2 different mixtures, theta and theta prime, whose first 6 moments are sufficiently close, they're within some epsilon to the c, that in fact implies that the parameters theta and theta prime are also close. It implies that there's a matching of the components in theta to a set of the components in theta prime, so that across this matching, we get the mixing weights right, we get the means right, and we get the variances right, within some additive epsilon. So this is, the core of what we need to prove in one dimension, is this stronger statement that not only 6 moments suffice, but that they robustly suffice, as it were. So hence, if we want to learn parameters that are close to the truth, the problem really is, how do we find estimates whose moments are sufficiently close to the true moments?
Is it like an implicit function theorem, or what?
There's a sense in which you can understand some of these stability results through projections of semi-algebraic sets, which I'll get into actually in the sequel when I explain Belkin and Sinha's work, which makes this more explicit. But we did this sort of directly, in fact. In any case, so this actually now yields an algorithm, because these 2 quantities of how close you need the moments to be and how close your parameters are in fact polynomially related. Because now the univariate learning algorithm is very simple to state. All you do is you take many samples from the underlying distribution, so that when you compute the empirical moments for r from 1 to 6, that with high probability, these empirical moments are very close to the true moments of the distribution, which will be true if I take enough samples. How close? Let's say within some epsilon to the c over 2. And now I have empirical moments which are sufficiently close to the true moments of the distribution, and all I have to do is find some theta prime, some setting of the parameters, so that his first 6 moments, which are now analytic functions of these parameters, are polynomials. Well, I want each of these moments to also be sufficiently close to the empirical moments for the first 6 empirical moments. How close? Again, within some additive epsilon to the c over 2. But the point of the previous slide was that it guarantees that when we find such a theta prime, whose moments are close to the empirical moments, which in turn are close to the true moments, that we're guaranteed that in fact theta prime is close to the true set of parameters. So theta prime must be close to theta precisely because solutions to these system of polynomial equations are relatively stable, that they satisfy some notion of a condition number. In fact, let me tell you about a more general approach to this problem due to Belkin and Sinha, which considered a more abstract and general framework in which you have some family of distributions, f of theta. And actually, it's sort of well known that under very mild conditions under this family, that in fact, two elements of this family, f theta and f theta prime, will be equal as distributions if and only if all of their moments are equal. A very tame conditions we need on this family in order for this to be guaranteed. So you can just forget about this if you want. But really, the crux of their definition is that this family f of theta will be called a polynomial family if the above condition holds. And furthermore, these moment functions are polynomials in the underlying parameters. So the expected value of x to the r, when it's taken from a member in this polynomial family, that quantity will be a polynomial in the underlying parameters we're trying to solve for. So namely, this contains, as a special case, for example, a mixture of Gaussians, a mixture of two Gaussians, a mixture of k Gaussians. These are all polynomial families. They're defined by their moments, and in fact, their moments are polynomials in the underlying parameters. Now, Belkin and Sinha's approach was first to define a set of polynomials, which are sort of moment difference polynomials. So q sub I will be a polynomial in the variables now. I'm treating both theta and theta prime as variables. It'll be a polynomial in these underlying variables. In fact, it'll just be the difference of this polynomial, the rth moment polynomial in theta, minus the rth moment polynomial in theta prime.
What is the I index there then?
Oh, sorry. Yeah, this should be r. Yeah, r. Good. So in fact, we can now use this set of polynomials to generate a sequence of ideals in the natural way. We have the first ideal, which is generated by the polynomials q1. So you take q1 and you apply all the properties of ideals. You're allowing multiplying by other polynomials and adding two elements and so on in the ideal. And then, well, that ideal is certainly contained by the second ideal, the one generated by q1 and q2 and so on. But because by Hilbert's basis theorem, polynomials, the ring of polynomials over the variables theta and theta prime is noetherian, we know, just by definition of noetherian, that there's no infinite increasing sequence of ideals. So after some point, these ideals all collapse. So for some value n, the ideal in equals in plus 1 equals in plus 2, and so on, forever. So what does this mean? And if you want to ignore the ideal language, then this is really what you should pick up on. Is the consequence of all of this is that we can express the difference polynomials using just the first n difference polynomials. That there's some coefficients which are themselves polynomials in theta and theta prime, so that this identity holds. So now what happens if we have two different members, if we have two members from this family, theta and theta prime? What happens if their first n moments exactly match? So this you should think of as being the analogous statement to showing that 6 moments of a mixture of two Gaussians suffice to uniquely determine the parameters. What happens if we have two different sets of parameters, theta and theta prime, so that their first n moments are exactly the same? This in turn implies that all of these polynomials on the right-hand side in this equation are all 0. So any higher order moment difference polynomials are also 0. So in fact, having the first n moments be exactly the same guarantees that all of your moments are exactly the same for theta and theta prime, which again, because this family is uniquely determined by all of its moments, that implies that the distributions are equal. F of theta equals f of theta prime. Or to put this in the contrapositive, if you assume that the two density functions are not the same, you're guaranteed that one of their first n moments must be different.
How is n determined as a function of the family?
It's not effective. I'll get to that. It's not effective. And that's a very critical thing. Maybe I should just state this so that you'll keep it in mind, is that these show that there is an algorithm. Because there's some finite bounds for these things, which these algorithms will provably work. But in general, you can't prove anything. It is.
Well, you can analyze this question for a specific distribution family, right? And then
Yeah. For example, you can plug in the bounds of 6 moments suffice into here. But in the general case, I still want to emphasize that the caveat that these are not effective bounds.
So can you show that 6
No, no, you can't. You can't because Hilbert's basis theorem is provably non-effective.
Even for like the specific polynomials that you get.
For the specific polynomials, then yes, you could use our earlier arguments to show that. But we can get into this later. I mean, an interesting case is just to look at the special case of Hilbert's basis theorem called Dixon's lemma. And that's a purely combinatorial statement in which it's very clear that there's no effective bound, even for polynomials in just two variables.
Yeah, if you try to prove it for other things, you end up basically just chasing around how many roots these differences have.
You end up chasing around the same thing.
Yeah.
In any case, so that's the first part of what they needed to establish, was that the first n moments for some n do indeed suffice for uniquely defining the parameters of this polynomial family. But in fact, we can now ask the analogy of the stability question of how stable these systems of polynomial equations are. And this part now I'm actually just going to sketch. But so the question we have is, we have two different sets of parameters, theta and theta prime. And we're guaranteed that the sum of their differences in the first n moments, that's at most delta. So their first n moments are very, very close, are within delta. Well, what's the smallest epsilon, as a function of delta, that we can take where we're guaranteed that necessarily theta is also close to theta prime? And actually, the key point is that this question can actually be formulated as a semi-algebraic set using the variables epsilon and delta and theta prime, it turns out. And this I will not go into detail on. But since it can be formulated as a semi-algebraic set, what is the smallest epsilon that we can take? What you can then do is you can project out these variables, theta and theta prime. And what you're left with is a set of polynomial constraints on just the variables epsilon and delta. So in fact, what this then implies is that epsilon is constrained by a polynomial in delta. So if you want to learn the parameters within some epsilon, it suffices to set delta equal to some polynomial in epsilon and learn the first n moments within that desired bound. And this, in exactly the same way, also yields a univariate learning algorithm, which is just the method of moments. Again, take many samples so that your first n moments are sufficiently close to the true ones, and find a setting of the parameters which matches it closely enough. And if you match it closely enough within this delta, you're guaranteed that your estimate parameters, theta prime, are close to theta.
Can I make a comment on this?
Uh-huh.
So this quantifier elimination is slightly reinventing the wheel. So this statement at the top, one way of saying this is, look, we have this polynomial, so we have these two sets of parameters, and we're asking when can the moments be the same. And when all the moments are the same, this is sort of a multivariate zero with this multivariate polynomial. And all we're asking is, can the function, namely the difference in these moments, can it linger near zero for a very long time near a root? Okay, so in one dimension, this is of a degree d polynomial. It has a root here. How close to zero can we be near zero? Well, only x to the d, if you're a distant x from a root. And in some sense, this is just extending that to this multivariate setting. How close to a multivariate root can we be?
It's also called, for example, the effective Voyashevich inequality for, in high dimensions. Voyashevich, who, Jano's collar is down the street. Anyways, this is actually all I wanted to say about learning mixtures of Gaussians, and actually now I'm going to move on to another example of when you can use systems of polynomial equations to design algorithms. And as I've already mentioned, this sort of caveat that this uses the basis theorem, so it's sort of ineffective. All you know is that there is an algorithm.
So for the case of mixtures of Gaussians, you can computationally check what the right bound is.
Actually, I tried that, and so actually I tried to encode this question as I wanted sort of a more, formulaic proof for 6 moments suffice, and I encoded it, and tried to solve it with an algebra solver, which does Grosvenor bases, and it never terminated. We can talk about that offline. Anyway, so the main theme that I wanted you to get, what's the take-home message, is that when you have the method of moments, oftentimes knowing moments about the underlying distribution forces the parameters to satisfy a system of polynomial equations. So always your first step should be showing that the system of polynomial equations only has the solution you're interested in. Its solution is only the true set of parameters. But then oftentimes you get actually algorithms that are somewhat noise stable precisely because these systems of polynomial equations are then themselves somewhat noise stable. And in fact, now what I'd like to tell you about is another problem in which systems of polynomial equations can be exploited for algorithmic purposes, and that's on the problem of computing the non-negative rank of a matrix. So what I'll be telling you about in the remainder of the talk is based on joint work with Sanjeev Arora, Rongji, and Ravi Kannan. So let me actually start off with a really dry definition of what the non-negative rank is, just to make sure we're all on the same page. And then I'll give you an example application to explain why it's important. So we have a matrix M, which throughout this talk, this matrix will be non-negative, entry-wise non-negative. And oftentimes we want to write M as the product of two matrices A and W. Moreover, we want to try and minimize what I'll call the inner dimension, which is equivalently the number of columns of A or the number of rows of W. And I'll call that the inner dimension throughout this talk. Now, what's the smallest inner dimension we can obtain here? That's just the rank of the original matrix. And there are, of course, efficient algorithms for computing a so-called rank factorization, one whose number of inner dimensions exactly matches the rank of M. But in the case where M itself is non-negative, oftentimes it makes sense to add constraints on A and W. Namely, since M is non-negative, we sometimes want that A and W are also non-negative, or also entry-wise non-negative. And then, in fact, the smallest value for the inner dimension we can obtain is called the non-negative rank. So the non-negative rank of a matrix M is the smallest R, so that M can be written as the product of non-negative matrices A and W, where the inner dimension is R. And let me get into that second. Let me give you a quick one sentence, and then let me actually show you an example. It's because oftentimes M, since it's non-negative, can be interpreted probabilistically. And then what you want is this factorization is essentially learning a model for the data, which you again want to interpret probabilistically. So that's why you want constraints of non-negativity on A and W. In fact, let me give you a very specific example. And this is something that's used throughout machine learning. In particular, this is used in information retrieval. Suppose we have some large collection of disorganized documents. And we want to cluster them according to what topics they're about. So the standard approach in machine learning is to form what's called a term-by-document matrix. So this will be a non-negative matrix. And every row in M will correspond to a different word that occurs somewhere in this database. And every column will correspond to a different document in the database. And the entry in the ith row and jth column is just the frequency of occurrence of the ith word in the jth document. So in fact, oftentimes you normalize M so that its columns have unit L1 norms. So every document we're thinking about as a distribution on words. And then this is a non-negative matrix, so you could ask, can you find a small inner dimension non-negative matrix factorization? And actually, as it'll turn out, actually I won't show this, but it turns out that you can also always assume that the columns of A have unit L1 norm and that the columns of W also have unit L1 norm. So every column in A is a distribution. Every column in W is a distribution. But now, because these are non-negative matrices A and W, we can actually interpret it in the language of probability. Namely, we can think of each column in A, since it's a distribution on words, as in a sense being a topic in the database. It's a distribution on words. And similarly, each column in W will be a representation of a document as a distribution on topics. Or to put this more formally, we have some column in M, which is a distribution on words. It's a document. And formally, this column can be expressed as the product of this column times this matrix. So what this means is we've expressed this document, which is a distribution on words, itself as a distribution on topics, which then when we take those topics as distributions on words, we exactly recover the original distribution. So what's interesting here is we have this large collection of disorganized documents, and finding a small inner dimension non-negative matrix factorization is akin to trying to explain these documents using a small number of topics, which then you can hope to do things like clustering based on the representation. So this is sort of the canonical approach within machine learning, and it has applications throughout machine learning. And really the punchline here is that non-negativity is what allows you to extract, to say that what you've learned is a probabilistic model, and you're trying to extract latent relationships that are present in the data.
About the previous slide, so you think that W could have negative entries somehow corresponding to being not in a topic?
Yeah, so in fact, one standard approach also is to instead compute the singular value decomposition, in which case the A and W that you find have negative entries. The issue is that then when you compare two documents' similarity, well, say one was about politics and one was about weather. They both won't contain the word elephant. So if there's some topic in here which is about animals, they'll both be slightly negatively correlated with that topic, which means in their representation they'll be slightly more correlated with each other because of the words they both omit. So the issue is that it doesn't capture the sort of additive nature of topics that we would want. And empirically, in many applications, non-negative matrix factorizations seem to work better. But of course, there's this trade-off that SVD is very computationally efficient. So the things that you can apply it on really is much, much larger than what you can do for non-negative rank. But that's a great question. In any case, non-negative matrix factorization is, in many cases, the model of choice in some specific applications. And things like image segmentation, text classification. In particular, maybe one of the most compelling applications is in the field of collaborative filtering. And in fact, it's even a very fundamental combinatorial parameter. It has applications to things like the notion of an extended formulation, where you have some polytope and you want to express it as the projection of a higher dimensional one. It turns out that the non-negative rank of an appropriately defined matrix is exactly how many facets you need in this higher dimensional polytope. Or it even has applications to things like the log rank conjecture of Lovaas and Sachs. And it also has applications in physical modeling. So I won't really give you any more details about applications, but what can we say about this problem computationally? So in fact, Vivesa showed that the non-negative rank is not as nice as its cousin, the rank. In fact, it's NP hard to compute the non-negative rank. But the way to interpret this result, it's not really as demoralizing as one would think. Because all it really tells us is that we can't hope for an algorithm that's polynomial in all the parameters of the problem. It's polynomial in n and m, the dimensions of the matrix, and also in R, the target inner dimension. But what I want to make as an observation with this example application to information retrieval in mind is that oftentimes the most interesting cases of non-negative rank are precisely when it's not too large. You can think about this as, in the case of a collection of documents. Well, what you really want to learn is you want to learn this non-negative matrix factorization precisely when it gives you a very small number of topics that together explain all the different documents in the database. So that's when it's most interesting, is when you've found a small number of hidden variables that explains all the data you've seen. And you can now ask, is there a way to sort of get around this hardness result? Maybe, in fact, there's a polynomial time algorithm for computing exactly does this matrix have non-negative rank at most R, which maybe is just not polynomial in one of the parameters. So it'll be polynomial in n and m and everything else, but it won't be polynomial in R, the number of topics. It'll be exponential in R.
So what's known about approximating this?
Nothing. Nothing.
Same answer.
Right, and actually, even for this exact question, this was, this was open. And actually, it turns out there's a exact polynomial time algorithm for every constant value for R. And actually, the approach will again be through a system of polynomial equations. OK, let me actually take a step back before I tell you about that. So let's start with an even more basic question. The answer to this question should actually not be obvious. Is non-negative rank even computable in the first place in any finite amount of time? And actually, it turns out that the answer is yes. It was observed by Kohn and Rothblum. And their approach was that they can formulate the question of does the matrix have non-negative rank at most R as a question about a system of polynomial equations, which actually, in turn, systems of polynomial equations can be solved in some finite amount of time. So that's how they showed the answer was yes. In fact, I'd like to take a slight detour into solving systems of polynomial equations, because that's where we can see some really fun, algebra and topology at play, is, the basic question in this area of solving systems of polynomial equations is we have something which is called a semi-algebraic set. And in turn, this set S is defined based on little s polynomials. So f1, f2, all the way up to fs, which in turn are polynomials in these k variables, x1 to xk. And in fact, what allowable choices for x1 to xk, these will be constrained by some Boolean function on the sign pattern of the different polynomials. So we have some Boolean function which takes as input the signs of these different polynomials evaluated on the choice of x1 to xk. And we'll only have the choices of x1 to xk that evaluate for this Boolean function to true. And actually, I'll make the following observation, which is that actually after a long, long line of work on this problem, the best known algorithms for finding a point in the set if it's non-empty, well, these algorithms, the main bottleneck turns out to be how many different sign configurations can you have of f1 to fs. And this is actually for a pretty simple reason, is that these approaches, through some very clever ideas, what they're able to do is they're able to enumerate the set of all sign configurations that arise for f1 to fs, and only those sign configurations, not too much more. So they check all the different sign configurations for f1 to fs, and then they make an oracle call to the Boolean function and check if it's true. And this is how they work. But now we have this quite, well, easy to state question, but it turns out that the answer is quite deep to this, is really how many sign patterns can arise as we range x1 to xk over all of space. In fact, the naive bound is exponential in s. In fact, I'll take the sign function to actually output -1, 0, or 1, and then the naive bound is like 3 to the s. Maybe every configuration of which polynomial is negative, which one's 0, and which one's positive could arise. And a really remarkable fact, due to Milner and Warren and again a whole sequence of authors before them, is that the number of sign patterns actually can't be this large. It's only exponential in the number of variables. And it depends only polynomially on the number of polynomials. So this is a really amazing theorem, and there's actually no known elementary proof of this. It's kind of remarkable that it's found so many applications in theoretical computer science, but there's no proof that doesn't go through Morse theory, in fact. And nevertheless, Renegard did show an algorithm that runs in roughly the same amount of time. He showed an algorithm for finding a point in the semi-algebraic set whose running time is exponential in the number of variables, but is polynomial in all the other parameters, polynomial in the number of polynomials and in the maximum degree. So now what can we say? Let's return to this original question, which we should hopefully be able to answer. So we have, this question is the non-negative rank even computable in the first place? Yep.
So can you go back to the previous slide? So given the theorem, why can't you just search like randomly? If you want to randomize algorithm that finds a point.
How do you find? How do you enumerate just the set of sign configurations?
But there aren't that many different sign configurations.
Uh-huh.
So you probably, so if you knew that.
But I mean, so you're searching in an exponentially large space for just this set of polynomially many sign configurations that do arise?
And you don't know that it's like uniform on the possible.
Yeah.
No, you do not know it's uniform.
If you can prove this theorem, you can probably prove that the probability that you're in each of these is it true that the probability that you're in any given one is so that most maybe.
What does probability mean? So you're defining a randomization over x1 to xk, which these components are very heterogeneous. The notion of what's the volume is oftentimes defined based on the cell in some algebraic language, and that's the rate of measure. I mean, these are that's still the same level of difficulty as going from here to here, in fact. Okay, so let me return to this question: is the non-negative rank even computable? And now actually the answer is yes, just due to Renegard's algorithm, is that we can create variables for the entries in A and W, which themselves, A is an M by R matrix and W is an R by N matrix. So the number of variables we have, one for each entry, is, it's N times R plus M times R. And now what we can do is we can write the constraints that A and W be entry-wise non-negative. These are just linear constraints on these variables. Moreover, we can also write the constraints that a times w is a valid factorization, that a times w equals m, and these in turn will be degree 2 constraints on these underlying variables. So here we have a system of polynomial equations which has a solution if and only if the non-negative rank of the original matrix is at most r. And in fact, then when we apply Rennegar's algorithm, well, the running time is exponential in the number of variables. But what I want you to remark here is that take r equals 3. This is exponential in the dimensions of the matrix still, even for very small values of non-negative rank. So in fact, this algorithm, Rennegar's algorithm, it gives us a very basic algebraic question we might want to answer, which is here we have a system of polynomial equations which encodes the question, does the matrix have non-negative rank at most r? Can we reduce the number of variables in the system of polynomial equations? Can we come up with some other system of polynomial equations which expresses the question, is the non-negative rank at most r, which uses much fewer variables, because that's really the biggest bottleneck in the running time.
Yeah. So your polynomial, each specific polynomial will only have 2r variables. So could it be that the previous result you showed actually depends on the maximum number of variables each polynomial individually?
It doesn't. Yeah, it doesn't. It's not. Yeah, it's not quite so simple. But there are ways to sort of use the extra polynomials you have to make the dependencies sort of create a long chain. This is even true in sort of the weak null Stellensatz and things like this, where the worst cases are actually just 2 variables per polynomial. Right. In fact, what I'm going to ask is, can we reduce the number of variables to being independent of the size of the original matrix? Can we reduce the number of variables to only a function of r? So in particular, what this would immediately give us, a positive answer to this purely algebraic question, would give us, in fact, for any constant value of r, we'd be using only a constant number of variables. So we could then solve this system in polynomial time. And there would be an exact algorithm for non-negative rank for every constant r. And let me actually start off with a much easier case. This will be way too easy compared to what the real theorem is, but this should at least get some of the ideas across. Is a very easy case is when the non-negative matrix A in this factorization itself has full column rank. And the reason it's easier is because now A has a pseudo-inverse. Some matrix, which when we left multiply by, we get the r by r identity matrix. In fact, what we can now do is we can multiply this entire equation on the right-hand side by this also missing matrix W. So the point is now I can group these two together, and that actually is data that I have. That's the matrix M, if this really is a non-negative matrix factorization. So what this is telling me is, knowing the pseudo-inverse A+, well, that gives us a linear transformation so that for every column of W, I can recover it as the linear transformation times the corresponding column in M. So we haven't really made too much progress right now, because this is still, if we treat the entries in A+ as variables, that's still too many variables. But now actually all we care about is A+'s action on the column space of M, which there at most are linearly independent columns. M better have rank at most r. So what we can do is we take M, we take a set of linearly independent, maximal linearly independent sets of columns, and all we care about is A+'s action on these columns. And so we can actually use these linearly independent columns to perform a change of basis, so that we change both A+ and this original matrix, so that this new linear transformation becomes much smaller. It becomes instead an r by r linear transformation, again, whose action on each column of M prime now recovers the corresponding column in W. So this is a way to reduce the number of variables, because now what if we had that both A and W in this factorization were both themselves full column rank and row rank respectively? Then all we have to do is we take the original matrix M, and we perform change of bases depending on the set of linearly independent columns or the set of linearly independent rows, and we get M prime and M double prime, which now we know that there are linear transformations S and T, which are themselves not too big. They're r by r, so that if we've suitably chosen these linear transformations applied to M prime and M double prime, which we know, will actually recover the matrices we want to find. They'll recover the non-negative matrices A and W, which now we can write the constraints that A and W be non-negative. This, in turn, is just a set of linear constraints on these variables in S and T. And in fact, even the constraint that A times W equals M is now just a degree 2 constraint on these underlying variables. So we have a system of polynomial equation and inequalities which has 2 times r squared variables who has a solution if and only if M has a non-negative rank at most r, and furthermore, that factorization is achieved by an A and W who have full column and row rank respectively. So this, in this very special case, would reduce the number of variables. But now let me tell you in closing just very briefly what we do, and I'll just sketch it, is what happens if A does not have full rank. So now the real difficulty is that A does not have a pseudo-inverse anymore. But in fact, what can save us is that we can consider all maximally linearly independent sets of columns of A. These alone do have pseudo-inverses. In fact, to put this in a picture format, what if the columns of A are here in the plane? Well, we know that the corresponding columns of M are all contained within the convex hull of the columns of A. So in fact, what we can do is for any, we can cover this with, things which we can compute pseudo-inverses for. We take this set of columns, the red ones, that does have a pseudo-inverse. We take this set of columns, this does have a pseudo-inverse. And now what we know is it turns out we can prove a structure theorem for non-negative matrix factorization so that these appropriately defined linear transformations will actually recover the corresponding entries of W. Namely, for every entry, every column in M, one of these 2 linear transformations will actually recover the corresponding column of W. Of course, the one technical issue is that what if I have this column right here, which maps to this entry? Well, if I apply the wrong linear transformation, so I try and represent it using these 3 elements, I'll get a negative value. So that won't be good. So in fact, in this case, what I want to use is the other linear transformation, which would recover a non-negative entry and vector, and that furthermore would be the corresponding vector in W. So in fact, it turns out that the choice function of which of these linear transformations to use, in turn, we can also show can be encoded as a system of polynomial equations. And all of this together gives us a way of reducing the number of variables down to a function of just r. In fact, the number of variables it'll be dominated by how many different linear transformations we can have. So we might need exponentially many in r, but it'll still be finite for any fixed r. So in this way, we get a polynomial time algorithm for every constant r. In fact, moreover, we can even show a compatible, a corresponding hardness result too, that in fact you can't do too much better. You can't hope for an algorithm which runs in time n times m to the little o of r, because in fact that would yield a sub-exponential time algorithm for 3-sat. So if you believe Russell's hypothesis, this isn't true. And I'll mention very briefly that in fact what I was recently able to do was to, even though you need exponentially many linear transformations, I can exploit algebraic dependence between them to actually reduce the number of variables even further down to just 2 times r squared. So in fact, this gives algorithms which are now singly exponential in the non-negative rank you're looking for. And regardless of how you try and solve it under reasonable complexity theoretic assumptions, you can't do too much better. So here the question of how fast an algorithm we can really hope to get for these problems is really revealed equivalently by how many variables we need in this system of polynomial equations.
So what if you try a different approach where you just take a random projection of the rows, right? So you know that, let's say you know this answer is going to have dimension r.
Mm-hmm.
Let's just project it to order of r rows. So you might expect then that you still be able to recover the matrix W correctly, which then you could just recover A.
Yeah, so I mean, so if you take something like the cross polytope, which has sort of exponentially many facets, so to cover it with linear transformations, you really need tons and tons of convex hulls of simplices. Then the issue is that in your recovery phase there, you're going to have a redundancy of which, you'll have a multiplicity of what the values of W could be. And actually, the issue is that it's not just any non-negative choice of W will work. You have to make sure that it's also compatible with the values you choose in A. So the issue is when you have like two linear transformations which cover the same thing, then how do you decide which of those two to choose? And really, I mean, that's part of the work in the theorem, is showing that that choice function can be encoded also using a system of polynomial equations. Right, so the sort of take-home message that I wanted you to get out of this last part of this talk was, in fact, that variable reduction can, in fact, be used as an algorithmic tool, that you can instead try and get better algorithms, even near optimal algorithms, just by asking, can I reduce the number of variables to something much smaller? So that's all I had, and all right, thank you.